The testing range fell silent. German engineers stood frozen, staring at what should have been impossible. Their finest armor plate, the same steel that protected their Tiger tanks, now had a clean hole punched straight through it. The captured American weapon was still smoking. One engineer picked up the penetrated plate, his hands trembling. They had tested it against their own MG-42, their 20mm cannons, even direct artillery fragments. Nothing had gone through like this. But this American machine gun, this M2 Browning chambered in .50 caliber, had torn through their best armor as if it were paper. It was 1943, and the Germans had just discovered they were facing a weapon that would rewrite the rules of armored warfare. A weapon so devastating that it would still be in service 8 decades later. A weapon that John Moses Browning had designed in a cramped workshop, never knowing it would become the most feared machine gun in history. This is the story of how American ingenuity created a legend, and how German engineers learned to fear the sound of the Ma-Deuce. Before we dive into this incredible story, hit that subscribe button and ring the notification bell. We're bringing you untold stories from World War II every week, stories that changed the course of history. And if you enjoy deep dives into military history, check out our playlist on weapons that define the war. Now, let's get into how a single weapon became the nightmare of the German war machine. Chapter 1: The Birth of a Legend. The year was 1918, and John Moses Browning sat in his workshop surrounded by blueprints and brass casings. The First World War was raging in Europe, and the United States military had come to him with an urgent request. They needed a heavy machine gun that could penetrate aircraft armor and stop vehicles. What they got would exceed every expectation. Browning was already a legend in firearms design. He had created the M1911 pistol, the Browning automatic rifle, and countless other weapons that had revolutionized warfare. But the M2 would become his masterpiece, a weapon so well designed that it would serve through every major American conflict for the next century. The challenge was significant. The military wanted a weapon that fired a much larger cartridge than standard infantry rifles, the .50 caliber BMG, Browning machine gun, round. This massive cartridge, measuring 12.7 by 99 mm, was designed to deliver devastating power at long ranges. Each bullet weighed nearly 2 ounces and could travel at speeds exceeding 2,900 feet per second. Browning approached the design with his characteristic genius for simplicity. He created a short recoil-operated, air-cooled machine gun that used a unique barrel extension system. The weapon's bolt would lock into the barrel extension, and as the gun fired, the barrel and bolt would recoil together for a short distance before unlocking. This system distributed the massive forces generated by the .50 caliber round, making the weapon surprisingly controllable despite its power. The first prototypes were completed in 1921, 3 years after the end of World War I. Browning himself wouldn't live to see his creation's full impact. He died in 1926 while working on another firearms project in Belgium. But his M2 design was so fundamentally sound that it required remarkably few modifications over the decades. Early testing at Aberdeen Proving Ground in Maryland revealed the weapon's extraordinary capabilities. Testers found that the M2 could maintain accuracy at ranges exceeding 2,000 yards, more than a mile. The kinetic energy of the .50 BMG round at these distances was still sufficient to penetrate light armor, disable vehicles, and devastate aircraft. The weapon's rate of fire was deliberately set between 450 and 600 rounds per minute, slower than many machine guns of the era. This wasn't a limitation but a feature. The slower rate of fire improved accuracy, reduced barrel wear, and allowed the operator to fire more controlled bursts. Each round was so powerful that volume of fire mattered less than precision. By the early 1930s, the M2 had been adopted across all branches of the U.S. military. The Army mounted them on vehicles and used them as anti-aircraft weapons. The Navy installed them on ships for defense against aircraft and small boats. The Marines carried them into combat as heavy support weapons. But no one yet understood just how devastating this weapon would prove against armored targets. The M2's design included several features that would prove crucial in combat. The quick-change barrel system allowed crews to swap out overheated barrels in seconds, maintaining sustained fire for extended periods. The adjustable headspace allowed the weapon to be fine-tuned for reliability in any environmental condition, from Arctic cold to desert heat. The sturdy tripod mount provided a stable firing platform that enhanced the weapon's already impressive accuracy. As tensions rose in Europe throughout the 1930s, American forces continued to refine their tactics with the M2. They discovered that the weapon's combination of power, range, and reliability made it invaluable for multiple roles. It could suppress enemy infantry at ranges where they couldn't effectively return fire. It could destroy light vehicles and fortifications. It could threaten aircraft at altitudes where smaller weapons were ineffective. What nobody fully appreciated yet was the M2's armor-penetrating capability. The .50 BMG round, particularly when loaded with armor-piercing incendiary ammunition, could defeat steel plate that stopped everything else. As German tank designers worked to create increasingly heavy armor for their panzers, they had no idea that American soldiers would be carrying a weapon that could punch through much of that protection. The stage was set. Europe was sliding toward war, and the Germans were building an armored force they believed to be invincible. Meanwhile, American soldiers were training with a weapon that would prove to be the Panzer's worst nightmare. The M2 Browning was ready for its moment in history, a moment that would come on the battlefields of World War II, where German engineers would learn a hard lesson about American firepower. Chapter 2, Blitzkrieg in the Armor Race. September 1, 1939. German panzers rolled across the Polish border, and the world witnessed a new form of warfare. Blitzkrieg, lightning war, combined fast-moving armored columns with close air support to overwhelm defenders before they could react. The tactic was devastatingly effective, and at its heart were German tanks that seemed unstoppable. The early German panzer force consisted primarily of Panzer I and Panzer II light tanks, along with some Panzer III and IV medium tanks. By modern standards, these vehicles were lightly armored. The Panzer II, for example, had frontal armor ranging from just 14.5 mm to 20 mm thick. The Panzer III featured 30 mm of frontal armor. This was considered adequate protection against the small-caliber weapons that dominated infantry arsenals of the time. German tank doctrine emphasized speed and maneuverability over heavy armor. Their commanders believed that fast-moving columns could avoid enemy strongpoints and exploit weaknesses before defenders could organize effective resistance. The armor was meant to protect against rifle fire and shell fragments, not to withstand sustained anti-tank fire. This doctrine proved spectacularly successful in the opening years of the war. Poland fell in weeks. Denmark and Norway were conquered. And in May 1940, German panzers smashed through French and British defenses, reaching the English Channel in just 10 days. The French had more and better tanks on paper, but German tactics and coordination carried the day. The success of Blitzkrieg created a sense of invulnerability around German armor. Wehrmacht propaganda celebrated the Panzer as an unstoppable weapon, and many German soldiers believed their tanks were invincible. Allied forces seemed helpless against the combined arms tactics that Germany had perfected. But the early victories masked a critical vulnerability. German tank armor, while effective against the weapons it typically encountered, was thin enough to be penetrated by heavy machine gun fire at close ranges. The Germans knew this theoretically, but they hadn't yet faced an enemy equipped with weapons capable of exploiting this weakness systematically. As the war expanded, German tank design began to evolve. The invasion of the Soviet Union in June 1941 brought German panzers face-to-face with Soviet T-34 and KV-1 tanks that featured heavier armor and more powerful guns than anything the Germans had previously encountered. This forced a rapid reevaluation of German tank design philosophy. The Panzer IV, originally designed as an infantry support vehicle, was upgunned and up-armored. New designs like the Panzer V Panther and Panzer VI Tiger were developed with much thicker armor. The Tiger I, which entered service in late 1942, featured frontal armor up to 100 mm thick, more than 3 times the protection of early Panzers. This armor race was driven primarily by the threat of Soviet anti-tank guns and enemy tanks. German engineers tested their armor against the weapons they expected to face: Soviet 45mm and 76mm anti-tank guns, British 2-pounder and 6-pounder guns, and various tank cannons. They calculated armor thickness based on defeating these threats at typical combat ranges. What German engineers didn't fully account for was the threat from heavy machine guns. The Wehrmacht's own heavy machine guns, the MG-34 and later the excellent MG-42, fired the 7.92 by 57mm Mauser cartridge. While deadly against infantry, this round lacked the energy to penetrate tank armor except under very specific conditions. German engineers assumed that enemy machine guns would be similarly limited. This assumption would prove costly. As American forces entered the war following Pearl Harbor in December 1941, they brought with them an infantry support weapon that German engineers hadn't properly evaluated: the M2 Browning .50 caliber machine gun. American troops began arriving in North Africa in late 1942 as part of Operation Torch. They came equipped with M2s mounted on vehicles, on ground tripods, and even some carried by infantry units as heavy support weapons. German forces in Africa, experienced and confident after years of desert warfare, initially didn't see these weapons as a serious threat to their armor. The first encounters changed that perception quickly. American soldiers discovered that the M2, particularly when loaded with armor-piercing incendiary ammunition, could penetrate the side and rear armor of German tanks at ranges up to several hundred yards. Even frontal armor on lighter panzers was vulnerable at closer distances. German after-action reports from North Africa began noting an unexpected threat: American heavy machine guns were destroying tanks. Intelligence officers initially dismissed these reports as exaggeration or confusion. Surely machine gun fire couldn't penetrate tank armor. But as more reports came in, accompanied by physical evidence from destroyed vehicles, German command took notice. Captured American equipment, including M2 machine guns and ammunition, was sent back to Germany for evaluation. Testing facilities in the Reich began systematic trials to determine exactly what this weapon could do. What they discovered would shock German tank designers and force a re-evaluation of their armor schemes. The tests showed that .50 caliber armor-piercing rounds could penetrate German tank armor at angles and ranges that shouldn't have been possible for a machine gun. The side armor of a Panzer III, just 30 mm thick, could be penetrated at ranges exceeding 500 meters. Rear armor, typically even thinner, was vulnerable at even longer ranges. Even some frontal armor sections could be penetrated at close range. This revelation came at a critical time. German industry was already struggling to produce enough tanks to replace combat losses on multiple fronts. Now they discovered that they needed to add more armor to protect against a threat they had never seriously considered. But adding armor meant adding weight, which reduced speed and mobility, the very advantages that German doctrine depended upon. Chapter 3: The Captured Weapon. The testing facility outside Berlin was cold and gray on the morning of February 1943. A group of Wehrmacht engineers and ordnance specialists gathered around a firing range that had been specially prepared for today's demonstration. On the firing line sat an American M2 Browning machine gun, captured in North Africa and shipped to Germany for evaluation. Hauptmann Friedrich Weber, a veteran tank officer who had served in France and Russia, was there to observe. He had read the preliminary reports about American heavy machine guns penetrating German armor, but he remained skeptical. After all, he had seen MG-34 and MG-42 fire bounce harmlessly off tank armor countless times. How could an enemy machine gun be so different? The test protocol was straightforward. They had arranged several armor plates at varying distances from the firing position. These plates represented the actual armor thickness used on German tanks: 14.5 mm for light vehicles, 30 mm for Panzer III side armor, 50 mm for Panzer IV frontal armor, and even an 80 mm plate representing Tiger I armor. The engineers would fire the M2 at each plate and document the results. The ammunition was equally important to the test. The Americans had captured several types of .50 caliber rounds, but the engineers were particularly interested in the M2 armor-piercing incendiary (API) round. This cartridge featured a hardened steel penetrator core with an incendiary compound behind it. When it struck armor, the penetrator would attempt to punch through while the incendiary material would ignite, potentially causing secondary damage inside the vehicle. Weber watched as the weapons technician loaded the first belt of ammunition. The M2 was mounted on a heavy tripod, secured firmly to prevent movement during firing. The first target was the 14.5 mm plate, representing the armor of reconnaissance vehicles and personnel carriers. It was positioned at 400 meters, a typical engagement range for infantry combat. The technician checked the weapon's headspace, adjusted the sights, and chambered the first round. The engineers retreated to a protected observation position. At the signal, the technician fired a short burst, 5 rounds. The sound was distinctive, different from German machine guns. The M2 had a slower, heavier report, a deep, authoritative boom rather than the high-pitched rip of an MG-42. Each shot was clearly distinguishable, giving the weapon a methodical, almost deliberate quality. The ceasefire order came immediately after the burst. Engineers rushed forward to examine the target plate. What they found made several of them stop and stare. 4 of the 5 rounds had struck the plate. 3 had penetrated completely, leaving clean holes with petalled edges where the metal had been pushed through. The 4th had nearly penetrated, creating a deep crater that had bulged the back of the plate outward. Weber felt the first stirrings of concern. Reconnaissance vehicles would be completely vulnerable to this weapon. But reconnaissance vehicles were lightly armored by design, everyone knew that. The real question was how the weapon would perform against main battle tank armor. The next target was the 30 mm plate at 300 meters, representing Panzer III side armor. This was more serious. The Panzer III was a mainline battle tank, a vehicle that had fought across Europe and Africa. Its armor should withstand machine gun fire easily. Another burst was fired, again, 5 rounds. This time the results were even more dramatic. 2 rounds penetrated completely. A third partially penetrated, with the penetrator lodged halfway through the plate. The impacts had generated significant heat, the edges of the holes were scorched and discolored. Weber's concern grew into alarm. The Panzer III side armor was vulnerable to machine gun fire. Any American infantry unit with an M2 could threaten a tank from the flank or rear. This meant German armor tactics would need to change. Tanks could no longer assume they were safe from infantry weapons except at the frontal arc. But the tests continued. The engineers moved to the 50 mm plate at 200 meters, representing Panzer IV frontal armor. Surely this would stop the machine gun rounds. 50 mm of hardened steel was substantial protection, designed to defeat anti-tank guns at typical combat ranges. The technician fired another burst. This time, only 1 round penetrated, but it penetrated completely. 2 others created deep craters without full penetration. The engineers examined the holes carefully, measuring the penetration depth and noting the damage pattern. The discussion among the engineers grew heated. One group argued that the single penetration was a lucky shot, that 50 mm armor was still adequate protection against machine guns. Another group pointed out that even 1 penetration could be catastrophic, it could kill crew members, damage critical equipment, or ignite ammunition. The armor was supposed to provide protection, and clearly it didn't, not reliably. Weber interrupted the debate. "Test it at closer range," he ordered. In combat, American infantry might get much closer than 200 meters, especially in urban terrain or forests. The 50 mm plate was repositioned at 100 meters. Another burst was fired. This time, 3 of 5 rounds penetrated. The evidence was undeniable. At close range, the M2 could defeat Panzer IV frontal armor. The implications were staggering. The final test was against the 80 mm Tiger I armor plate, positioned at 100 meters. This was the Wehrmacht's heaviest operational tank, a vehicle designed to be nearly invulnerable to enemy fire. Surely the Tiger's massive armor would stop the machine gun. The burst struck the plate with a different sound, louder impacts, but no clean penetrations. The engineers examined the plate and found deep craters, some penetrating more than halfway through the 80 mm thickness. At this range, the M2 couldn't fully penetrate Tiger armor, but the damage was still concerning. The repeated impacts in the same area might eventually breach the armor, and the shock from the impacts would be transmitted to the crew and internal components. Weber stood silently, processing what he had witnessed. The American M2 Browning wasn't just another machine gun, it was a genuine threat to German armor. Tanks that the Wehrmacht had assumed were safe from infantry weapons were now vulnerable to a weapon that was apparently common in American units. Chapter 4: The Battlefield Reality. Staff Sergeant James Mitchell crouched behind his M2 Browning, watching the German half-track through his sights. It was June 1944, 3 weeks after D-Day, and his unit was pushing inland through the Norman hedgerows. The half-track was supporting German infantry, its mounted machine guns sweeping the field and keeping Mitchell's company pinned down. Mitchell's assistant gunner, Private Rodriguez, had already loaded a belt of armor-piercing rounds. They had learned quickly in combat that the M2 wasn't just for suppressing enemy infantry, it could kill vehicles too. Mitchell had knocked out 2 German trucks and a Kübelwagen in the past week. But a half-track was more substantial prey. Range? Mitchell asked, keeping his voice low. 300 yards, Sarge. Maybe a bit less, Rodriguez replied, peering through binoculars. Mitchell adjusted his aim slightly, leading the target as the half-track moved across the field. He squeezed the trigger, and the M2 roared to life. The tracer rounds arced across the field, and he could see them impacting the half-track's armor. He fired in controlled bursts, walking his fire across the vehicle's side. On the 4th burst, something changed. Smoke began pouring from the half-track's engine compartment. The vehicle lurched to a stop, and German soldiers began bailing out, desperate to escape before the vehicle caught fire. Mitchell shifted his aim to the dismounting troops, then thought better of it. They were running away from the fight, and his primary mission was to eliminate the vehicle threat. Moments later, flames erupted from the half-track's interior. Secondary explosions, probably ammunition cooking off, tore through the vehicle's thin roof armor. The German infantry that had been using it for cover scattered, and Mitchell's company was able to advance. This scene played out countless times across the European theater in 1944 and 1945. American forces, equipped with M2 machine guns mounted on jeeps, half-tracks, tanks, and ground tripods, discovered that they could engage German armor with a weapon that was supposed to be used against infantry and aircraft. The psychological effect on German troops was significant. Lieutenant Hans Becker, commanding a Panzer IV in Normandy, recorded his experience in a letter home that was later captured by Allied forces. The Americans have a terrible heavy machine gun. It sounds different from our weapons, slower, heavier. When you hear it, you know to keep your tanks front toward the enemy. We lost Hauptmann Werner's tank last week when they hit it from the side. The rounds went straight through the armor. 3 of his crew died before they could escape. The tactical implications were profound. German armor doctrine had always emphasized maneuver and combined arms tactics. Tanks were supposed to operate with infantry support, and infantry were equipped with weapons that could threaten enemy infantry and light vehicles, but not tanks. The M2 changed that calculation. American infantry units with M2s could now threaten German tanks, especially from the flanks or rear. This forced German armor to be more cautious, to expose fewer angles to potential attack, to avoid certain terrain where heavy machine guns might be concealed. The invulnerability that early war panzers had enjoyed was gone. The M2's effectiveness varied depending on the target and circumstances. Against light vehicles like the SD, KFC, 251 half-track, the weapon was devastating at almost any angle and reasonable range. Against medium tanks like the Panzer IV, side and rear shots at ranges under 500 yards could achieve penetration. Against heavy tanks like the Tiger and Panther, the M2 typically couldn't penetrate frontal armor, but side and rear shots at close range remained dangerous. Perhaps most importantly, the M2 could target the vulnerable spots on all German vehicles. Vision ports, which had to be relatively thin to serve their purpose, were vulnerable. Engine grills and air intakes could be damaged, causing overheating and mechanical failure. Track systems could be damaged, immobilizing the vehicle. Even when the M2 couldn't penetrate armor directly, sustained fire could still mission-kill a vehicle. American commanders quickly learned to integrate the M2 into their anti-armor tactics. In defensive positions, M2s would be sighted to provide enfilade fire against any German armor attempting to assault the position. The flanking position maximized the weapon's armor-penetrating capability while making it difficult for the German tanks to return effective fire. In urban combat, M2s proved particularly valuable. The close ranges typical of city fighting played to the weapon's strengths. American forces would position M2s in upper-story windows or on rooftops, giving them angles to fire down onto the thinner top armor of German vehicles. Several Tigers and Panthers were knocked out in this manner during the fighting in France and Germany. The weapon's long range also proved tactically important. The M2 could engage targets at distances where German tank cannon fire was less accurate. While a tank gun might score a one-shot kill at any range, it still had to aim and fire carefully. The M2 could put dozens of rounds into the target area, increasing the probability of hitting a vulnerable point. German tank crews reported that sustained .50 caliber fire was terrifying even when it didn't penetrate. The hammering impacts on the armor were deafening and disorienting. American vehicle crews loved the M2 for its versatility. Tank destroyers and light tanks often mounted .50 caliber machine guns as secondary armament. These proved invaluable for engaging soft-skinned vehicles, suppressing enemy infantry, and threatening the flanks of enemy armor. The commander of an M10 tank destroyer could use his .50 cal to keep enemy infantry away from his vehicle while the main gun dealt with enemy tanks. German forces adapted their tactics in response to the M2 threat. Tank commanders learned to keep their vehicle's frontal armor towards suspected enemy positions whenever possible. Infantry support for armored units was increased to help spot and suppress M2 positions. German forces began targeting American machine gun positions with artillery and mortars more aggressively, recognizing them as legitimate threats to armor. Chapter 5: The Engineering Response. By late 1943, German military planners faced an uncomfortable reality: their armor was vulnerable to American heavy machine guns in ways they had never anticipated. The question became what to do about it. The engineering response revealed both the strengths and limitations of German war production under increasing pressure. The most obvious solution was to increase armor thickness across all German armored vehicles. However, this approach faced immediate practical obstacles. German industry was already struggling to meet production quotas for existing tank designs. Adding more armor meant adding more weight, which required more powerful engines, stronger transmissions, and more robust suspension systems. Each modification cascaded into additional complexity and cost. The Panzer IV provides a clear example of this challenge. The original 1937 design featured a combat weight of about 20 tons. By 1943, various up-armoring modifications had increased this to nearly 25 tons. The tank's original engine and transmission were barely adequate for this increased weight. Adding enough armor to reliably defeat .50 caliber fire would push the weight even higher, potentially making the vehicle underpowered and unreliable. German engineers explored several technical solutions. One approach was to use spaced armor, mounting thin armor plates with gaps between them. The theory was that this would cause armor-piercing rounds to tumble or fragment after penetrating the first layer, reducing their effectiveness against the main armor plate. Testing showed this could be effective, but it added significant complexity to manufacturing and made the vehicles wider, a problem for rail transport and maneuverability in restricted terrain. Another approach was to use face-hardened armor, with an extremely hard outer layer backed by tougher, more ductile steel. This provided better protection per unit thickness against armor-piercing rounds. However, the heat treatment process required for face hardening was time-consuming and required specialized facilities. As the war progressed and German industry came under increasing air attack, maintaining the sophisticated heat treatment processes became difficult. The Panther tank, entering service in mid-1943, incorporated some lessons learned from the M2 threat. Its side armor was increased to 40 mm from the 30 mm of the Panzer III, and it was sloped at an angle that increased effective thickness against perpendicular fire. However, even this wasn't enough to provide immunity against .50 caliber fire at close ranges. The armor could still be penetrated at ranges under 200 meters when hit at favorable angles. The Tiger II, developed in 1944, represented the ultimate expression of the more armor approach. Its frontal armor was 150 mm thick, and even side armor ranged from 80 mm to 100 mm. This vehicle was essentially immune to M2 fire from any angle at any practical range. However, it weighed 68 tons, suffered chronic mechanical problems, and was produced in tiny numbers, fewer than 500 total. It was a technical showcase rather than a practical solution to the armor vulnerability problem. German military planners also pursued tactical and operational responses. New training emphasized keeping vulnerable tank surfaces away from enemy positions. Tank commanders were instructed to use terrain more carefully, positioning vehicles hull down whenever possible to minimize exposed surface area. Infantry support for armor was emphasized even more strongly to suppress enemy machine gun positions before they could engage tanks effectively. But these solutions all shared a common limitation: they addressed the symptom rather than the cause. The fundamental problem wasn't that German armor was too thin, it was that American infantry possessed a weapon with capabilities far beyond what anyone had expected from a machine gun. The .50 BMG cartridge delivered energy levels that approached small cannon rounds, and the M2's accuracy and reliability made it effective at ranges where most machine guns struggled. German engineers did evaluate their own heavy machine guns as potential counters. The Wehrmacht had developed the Panzerbuchs 41 anti-tank rifle and various heavy machine gun designs, but none matched the combination of power, reliability, and portability of the M2. The German 13mm MG-131, developed as an aircraft weapon, came closest in power, but it was never widely deployed as a ground weapon. Some German units captured M2 machine guns and pressed them into service. These weapons were highly prized, and units that possessed them guarded them carefully. However, ammunition supply was a constant problem. Germany didn't manufacture .50 BMG ammunition, so captured weapons could only be used until their captured ammunition was exhausted. Some German troops reported that the distinctive sound of an M2 actually worked in their favor. When they fired captured .50 calories, American forces sometimes hesitated, thinking the fire was friendly. The most revealing aspect of the German response was what it revealed about industrial priorities under pressure. By 1944, German war production was focused on building vehicles that could counter Soviet heavy tanks, particularly the IS-2 and the improved T-34-85. The .50 caliber vulnerability was a known problem, but it competed for attention and resources with many other urgent needs. German generals and engineers had to make hard choices about resource allocation. Should they devote precious manufacturing capacity to adding armor that protected against American machine guns, or should they focus on building more vehicles with existing protection levels? Should they develop new weapons to counter the M2 threat, or prioritize anti-tank weapons to deal with ever-improving Allied armor? In practice, the German response was piecemeal and inadequate. Some units received reinforcement armor kits that could be field welded onto vulnerable areas of existing tanks. Some new production vehicles incorporated thicker side armor. But a comprehensive solution never emerged. German industry was simply too overwhelmed by competing demands and too disrupted by Allied bombing to implement a systematic response. Chapter 6: Legacy of the Ma-Deuce. The M2 Browning machine gun earned its nickname Ma-Deuce during World War II, and by war's end, it had established a reputation as one of the most effective weapons in the American arsenal. But the weapon's story didn't end in 1945, it continued through every subsequent American conflict and remains in service today, more than a century after John Browning conceived its basic design. The Korean War saw the M2 employed in much the same roles as in World War II. American forces used it as a vehicle weapon, an anti-aircraft gun, and a heavy infantry support weapon. Chinese and North Korean forces, many equipped with Soviet armor similar to the German vehicles the M2 had proven effective against, learned to respect the weapon's capabilities. The battle-tested tactics from World War II transferred directly to the Korean Peninsula. In Vietnam, the M2 found new applications. It was mounted on river patrol boats, where its long-range and armor-penetrating capability proved valuable against fortified positions along riverbanks. It was installed on helicopters, where its reliability in harsh conditions and devastating firepower made it a preferred door gun. And it continued its traditional role as a vehicle weapon, mounted on jeeps, trucks, and armored personnel carriers. The weapon's ability to engage lightly armored vehicles remained relevant throughout the Cold War. Soviet-designed BTR and BRDM armored personnel carriers had armor thickness comparable to World War II German light armor, and the M2 could defeat them at similar ranges. This gave American infantry units equipped with M2s a genuine capability against Soviet mechanized forces. Modern conflicts have proven the M2's enduring value. In Iraq and Afghanistan, the weapon has been employed against everything from insurgent vehicles to fortified positions. Its ability to penetrate walls and cover that stop smaller caliber weapons has made it invaluable in urban combat. The psychological effect of .50 caliber fire remains significant. The weapon's distinctive sound and visible impact on targets has a morale effect that goes beyond its physical damage. The technical longevity of the M2 design is remarkable. While the basic action has remained essentially unchanged since Browning's original design, detail improvements have continued throughout the weapon's service life. Modern M2s feature quick-change barrel systems that allow the barrel to be swapped in under 10 seconds without adjusting headspace. Soft-mount systems reduce the shock and vibration transmitted to vehicle crews. Modern ammunition with improved penetrators extends the weapon's armor-defeating capability even further. Perhaps the most striking testament to the M2's design excellence is how few attempts have been made to replace it. While almost every other World War II-era weapon has been retired or replaced by more modern designs, the M2 continues in frontline service. Various replacement programs have been proposed over the decades, but none has resulted in widespread adoption of a new weapon. The M2 simply does its job too well to justify the enormous cost of replacing the millions of weapons in service worldwide. The weapon's versatility has proven to be one of its greatest strengths. The same basic weapon can be mounted on a ground tripod for infantry support, on a vehicle pintle mount, on aircraft, or on naval vessels. It can use a variety of ammunition types optimized for different targets, armor-piercing for vehicles, incendiary for fuel tanks and aircraft, and even specialized rounds for explosive ordnance disposal. This versatility means that logistics chains don't need to support multiple weapons and ammunition types for different roles. Modern militaries around the world continue to field the M2 or license-built variants. Beyond the United States, countries including the United Kingdom, Canada, Israel, South Korea, Japan, and dozens of others maintain the weapon in their arsenals. The total number of M2s manufactured since 1921 is estimated to exceed 3 million, making it one of the most widely produced heavy machine guns in history. The German engineers who tested captured M2s in 1943 would probably be astonished to learn that the weapon they evaluated would still be in service 8 decades later. But they would understand immediately why it has endured. They witnessed firsthand the weapon's remarkable effectiveness. The clean holes punched through armor plate that shocked them during testing have been replicated millions of times in combat around the world. John Moses Browning died in 1926, never seeing his M2 design employed in combat. He never knew that his creation would serve through World War II, Korea, Vietnam, the Gulf War, Iraq, Afghanistan, and countless smaller conflicts. He never knew that soldiers in 2025 would still be carrying essentially the same weapon he designed in 1918. But he would recognize the weapon instantly. The basic design is that fundamentally sound. The M2's story illustrates several important principles about weapons design. Reliability matters more than complexity. Simple, robust mechanisms that can be maintained under field conditions will outlast sophisticated systems that require specialized support. power matters, the .50 BMG cartridge provides capabilities that smaller rounds simply cannot match, and that power remains relevant across changing tactical circumstances. And good design endures. Browning's basic action, with its short recoil operation and barrel extension locking system, solved the fundamental challenge of harnessing .50 caliber power in a manageable package. When German engineers saw that armor plate with clean .50 caliber holes punched through it, they were witnessing more than just effective weapon design. They were seeing a weapon that would define heavy machine gun design for a century. The M2 Browning, the Ma-Deuce, has earned its place as one of the most successful and enduring weapons in military history. And somewhere, perhaps, John Moses Browning would be quietly satisfied to know that his design got it right the first time. Epilogue: the weapon that refuses to die. There's a photograph from 2023 that perfectly captures the M2's extraordinary longevity. It shows a U.S. Marine Corps gunner manning a .50 caliber machine gun on a patrol in an undisclosed location. The weapon is mounted on a modern armored vehicle bristling with digital communications equipment, thermal optics, and sophisticated defensive systems. But the M2 itself would be instantly recognizable to a soldier from 1944. The basic silhouette, the barrel, the receiver, all fundamentally unchanged from John Browning's century-old design. This endurance is unprecedented in military history. Consider that in the same time frame the M2 has served, military rifles have evolved through multiple generations, from bolt-action to semi-automatic to select-fire assault rifles. Artillery has transformed from towed guns to self-propelled systems with computerized fire control. Aircraft have progressed from propeller-driven fighters to supersonic jets to stealth technology. Yet the M2 remains, outlasting every contemporary weapon system. The secret to this longevity isn't mysterious, it's simply that Browning solved the fundamental engineering problem so elegantly that no one has found a significantly better solution. The weapon's short recoil operation efficiently manages the massive forces generated by the .50 BMG cartridge. The air-cooled barrel eliminates complex water cooling systems. The belt feed mechanism is reliable and fast. The basic action is simple enough that it can be maintained under primitive field conditions, yet robust enough to fire hundreds of thousands of rounds over its service life. Modern ammunition technology has actually extended the M2's capabilities beyond what Browning could have imagined. New armor-piercing rounds with tungsten or depleted uranium penetrators can defeat armor that would have seemed like science fiction in 1918. Specialized ammunition includes saboed light armor penetrators, multipurpose rounds that combine anti-personnel and anti-material effects, and even programmable ammunition for specific tactical situations. The weapon platform remains unchanged, but the ammunition continues to evolve. The economic logic of the M2's continued service is compelling. The U.S. military alone maintains an inventory of over 50,000 M2 machine guns. Replacing them with a new weapon system would require not just purchasing new guns, but also retraining hundreds of thousands of soldiers, developing new ammunition production lines, establishing new logistics chains, and adapting thousands of vehicle and aircraft mounting systems. The cost would be measured in billions of dollars. And for what benefit? The M2 already performs its mission exceptionally well. Various replacement attempts have been made over the decades. In the 1980s, there was interest in developing a lighter .50 caliber weapon using more modern materials and manufacturing techniques. Prototype weapons were built that weighed significantly less than the M2's 84 pounds. But testing revealed that the weight reduction came at a cost. The lighter weapons suffered increased recoil, reduced accuracy, and questions about long-term durability. The program was eventually abandoned. More recently, programs have explored smart ammunition and guided projectiles for heavy machine guns. These systems promise dramatic improvements in accuracy and effective range. But they're designed to work with existing M2 weapons. Once again, the basic platform proves so sound that it makes more sense to enhance it than replace it. The M2's combat record speaks for itself. Every American service member who has deployed to a combat zone in the past 80 years has known the reassuring presence of the Ma-Deuce. They've seen it punch through walls that stop rifle fire. They've watched it disable vehicles at ranges where other weapons struggle. They've felt the psychological comfort of having overwhelming firepower available when needed. That intangible confidence factor, knowing you have a weapon that can handle almost any threat, is difficult to quantify but impossible to dismiss. The weapon has become so iconic that its sound alone carries meaning. The distinctive Modus rhythm of .50 caliber fire is instantly recognizable to anyone who has served in combat. That sound means friendly fire superiority. It means American forces are present. Enemy combatants from World War II to modern conflicts have learned to recognize and fear that particular cadence of heavy thumping fire. There's poetry in the fact that German engineers in 1943, testing this captured American weapon, were evaluating something that would outlast their entire military, their entire government, and their entire conception of warfare. The armor they were so concerned about protecting has long since been scrapped or placed in museums. The tanks they designed are historical curiosities. But the weapon that punched through their armor plates is still in frontline service, still doing the same job it was designed for over a century ago. John Moses Browning's legacy extends far beyond the M2. His designs include the M1911 pistol, still widely used today, the Browning automatic rifle, the Browning high-power pistol, and numerous shotguns and sporting rifles. But the M2 represents perhaps his greatest achievement, a weapon so fundamentally well-designed that it has required virtually no modification across a century of technological change. As we look to the future, it seems likely that the M2 will continue in service for decades to come. Modern infantry combat still requires a heavy support weapon that can defeat light armor, suppress enemy positions at long range, and provide psychological deterrence. The .50 caliber cartridge still delivers unmatched power at ranges where it matters. And the M2 action still manages that power more reliably than any alternative design. The next time you see footage of American military operations anywhere in the world, look for the distinctive profile of the M2 Browning. It will be there, mounted on vehicles or ground positions, doing exactly what it was designed to do in 1918. That stubby barrel, that rectangular receiver, that methodical rate of fire, unchanged and still deadly effective. The German engineers who witnessed those test fires in 1943 saw the future, though they couldn't have known it. They saw a weapon that would outlast their Reich, outlast their war, outlast their entire generation. They saw American engineering at its finest, simple, powerful, reliable, and built to last. They saw the Modus, and history would prove them right to be concerned. The weapon that shocked them by punching through German armor continues to serve, ready to punch through whatever challenges the next century brings.